I chose this paper. I think it's a good opportunity to talk to people that know a lot more than I do about the technical stuff. So I might not be able to answer to your questions, all of your questions at the end of the presentation when it comes to implementation and so forth, but I think there are some pretty interesting intuitions in this paper. And I wanted to discuss these intuitions with technical people. Like you are the ones who know really about this. So let's see. So basically this paper is called a case-based interpretable deep learning model for classification of mass lesions in digital mammography. And in this paper, the authors deal with computer vision for deciding whether to order a biopsy based on a mammographic exam. So there's a mammographic exam, they already identified a lesion, and it's a matter of classifying in a multi-class classification, classifying the mass margin type through computer vision for deciding whether there is a high probability of this lesion of being malign or not. So the challenge here is that data sets are small and there's confounding information. Basically, the ML-driven system focuses sometimes on medically non-relevant features for making a prediction. So the authors want to tackle this problem from different lenses. So they tackle from the data side, kind of. They also create a novel interpretable neural network based on case-based reasoning, and they also deal with the explanation part. So I will, I will dive deep into each of these parts afterwards, but just so that you have an idea, in the case of the data, they use a hybrid approach of data annotation. They have a coarsely annotated data set and a fine annotated subset within that data set, where there is a pixel-wise annotation so that they can ensure that the model is focusing on medically relevant features when making a prediction. When it comes to the model itself, instead of using a black box model, the authors claim that in high stakes domains, it is necessary for these models to be interpretable. And they use this kind of case-based reasoning. They claim that it's important that the deep learning model kind of follows the reasoning process of the radiologists themselves, who usually give a diagnosis based on comparison and similarity, basically. So that's what they do. They create this similarity-based reasoning process for the deep learning model. And since the model itself is interpretable, they don't need to use post hoc explanations to explain the reasoning process of the model, but basically they end up with some activation maps, which are the similarity maps between the input image and the prototypical example of one mass margin type. So that's like the very quick summary of what they do. They claim that their contribution is that these classifications are made based on clinically relevant information and kind of following the radiologist's reasoning process. So if the reasoning process is correct, this model could generalize beyond its finite training set. They also claim that this would lead to better human-machine collaboration, although there's no user test or anything like that to prove it. But they claim that since the model's reasoning process is aligned with the reasoning process of the radiologists, this would lead to better human-machine collaboration. They also claim that it's easier to troubleshoot and to evaluate the trustworthiness of the model, since we are kind of forcing the model to focus on clinically relevant information for making a decision if the activation map is beyond that finely annotated area. It's easier to identify when the model is focusing on features which are not relevant for making a prediction. And they also claim that the model's reasoning reporting process could be aligned with the structured lexicon that radiologists use to report results. So that's the summary of what they do. When it comes to the data, as I mentioned, they kind of use a hybrid data annotation process. On the one hand, they've got coarsely annotated data. So for us, like there are three different classes that they will work with: the speculated class, indistinct, and circumscribed. So in the case of the microlobulated class, they exclude it this class because the sample was too small. And in the case of the obscured class, it's not a good indicator for classifying whether a lesion is malign or not. So they also excluded this class. So basically there will be 3 different classes, each of them crossly annotated. And they used data augmentation for having 5,000 data instances of each of these classes in the training set. And well, since the data set is not very big, they use a typical 73, 12, 15% of training, validation, and testing. In the case of the finely annotated data, within this data set, they use a small subset with fine annotations, and they create this fine annotation mask, MI, where 0 means that those pixels are medically relevant for making a prediction, and 1 means that those pixels are medically irrelevant for making a prediction. So they kind of force the focus, the model to focus on relevant features for making a prediction. And yeah, they do it through this fine annotation mask. When it comes to the model itself, well, this is the architecture. The first layers are the convolutional layers, where they extract features for mass margin classifications, and these layers are pre-trained on ImageNet. They then follow with the prototype layer, which is what makes the whole thing different and interpretable. And this prototype layer is learned from the training set. So they have M prototypes, and each prototype is basically a 1-by-1 patch with the same number of channels as the convolutional, as what we get at the end of the convolutional layers. And these prototypes represent a prototypical activation patterns of its class. So for the case of spicules, these are spiculated masses. For indistinct masses, these are fuzzy borders. And for circumscribed masses, these are clearly defined borders. So basically, it's a prototypical representation of what a mass margin type, a certain mass margin type, looks like. And what they basically do is kind of drag, or I imagine it like dragging. Our input feature would have 14-by-14 patches. So each of those patches is compared to the prototypical example, and they compute the L2 distance to know how similar the patch within this input image is to the prototypical representation of that mass margin type. And they create a spatially arranged similarity map between the input image and the prototypical example. So then these goes into this following step, where the similarity map, the spatially arranged similarity scores, are upsampled, and we end up basically with this kind of heat maps where where the representation is basically the parts of the input image that are most similar to the learned prototype. And in order to translate this similarity map into one similarity score, they pick the K highest similarity scores and compute the average. So this similarity score will define how strong a prototypical feature is present within the K most activated parts of the input image. So then they go from the similarity score to the probabilities of this input image belonging to each of the different classes, and the probability of that feature or that lesion, of being malign. So they do this with fully connected layers. The first fully connected layer basically multiplies the similarity scores we get from the previous steps by a weight matrix, and this goes into a submap function so that we normalize and generate the probabilities of a mass margin type to belong to one of the three mass margin types. And H2, what it does is to use a normalized mass margin score. So this is not an end-to-end training, of course, and a normalized mass margin score into a final score of malignancy. So that's more or less like the architecture that they use. And of course, the training kind of procedure is a little bit complicated. They already acknowledge it within the paper that the training has 4 different steps: A1, A2, A3, and a separate training B step, kind of. So when it comes to the training, in order to incorporate this kind of hybrid data annotation practices and so forth, they use a custom kind of loss function. So in the first step, they jointly optimize the parameters of the convolutional layers, and they learn, they make the model learn these prototypes. So there are like 4 different elements within this loss function: the typical cross entropy, which penalizes a misclassification of margin types. There is a cluster cost and separation cost, which forces each of these convolutional features that represent a particular mass margin type to be clustered around a certain prototype. So we could imagine this as a model interpretability technique, where you have clusters around the prototypical examples of each of these features. And there's a fine loss element as well, which is the one that forces, that penalizes the focus of the model being outside the finely annotated region. So it ensures that the learned features are medically relevant. So that's like the first step of the training. The second step of the training projects the prototypes to the nearest feature patch from the training set D. So this paper is a continuation of another paper which was published in 2019, I think, in NoDips, where they they go deeper into how this projection step looks like. And then there's a training A3 where they fine-tune H1, the first fully connected layer, and a separate training step B where they train H2. So as I mentioned, in H1, they use this softmax layer to normalize the similarity scores into probabilities of these lesions to belong to each of the mass margin types. And in H2, they use the unnormalized similarity scores to get this malignancy probability. So these are 2 separate training steps where there is no return from stage A, from stage B, sorry, to go to stage A. So that's, there are more details in the paper about the training, but well, that's like the overview of the training. And when it comes to explainability, or well, the model is itself interpretable. So they claim, the authors claim, that this approach is more appropriate for high stakes domains where it's not enough to have an interpretable approach, or an approach only based on attention where there is no other context provided. So they claim that their own approach, where you can see the reasoning, you can see the final prediction, of course, but you can see how each of the parts or patches of the input image has been compared to prototypical examples and given a similarity score and a certain weight when it comes to getting to this final prediction. So they claim that this approach, although it's more expensive, of course, when it comes to getting finely annotated data, when it comes to training the model like this in a modular fashion, they claim that it's necessary in high stakes domains to have this certainty of knowing what's happening, or the reasoning process of the model itself. So this is how, or what what their explanation kind of would look like. Of course, they also kind of measure how interpretable the model is. So basically, they calculate, or they create this activation precision metric, where they calculate which of the upsampled or the activation maps that we saw, the heat maps that we saw, which of those pixels really belong to the clinically relevant part, so that there is a precisely bounded area that the model is focusing on. And when it comes to the results, they say that their interpretable model can perform as well as some other non-interpretable models. And additional to that, they do have this interpretability that that ensures that kind of the reasoning process is transparent, kind of. So that's what I wanted to talk about, and I want to know your opinion. I think there are some interesting intuitions here, but yeah, I would like to know your opinion as well.
Well, first off, thank you for that. That was actually very, very interesting. I agree there's some clear intuitions there, but one of the things that wasn't readily clear from going through like their model and their process and I don't necessarily expect you to know an answer to this, but I'm curious about it, is how would this model handle a situation where there's more than one malignant space in a single image that it's analyzing? Does it focus on just one of them, or is it capable of actually identifying multiple, breaking it out and passing it through its pipeline? I couldn't quite follow along with the way that it was convoluting the images, I guess is the term, to see if it would be able to handle multiple pieces, because it seems like all of the examples, there's only like a single one, right?
As far as I understand, what they do is, so they do compare the input image and calculate the similarity scores with each of the prototypical examples, and they get a similarity map and a final similarity score for each of those mass margin types. So in the end, there is a kind of final malignancy probability that comes from each of those similarity scores with respect to a mass margin type, contributing differently to this final malignancy score.
Okay. Do you know if any of those mass margin types, so like on the slide that you're on right here, we can see that there's, in the heat map, there's like one central area, which is what this model is focusing on. Do we know if any of the prototypical mass margin images that these similarities are being compared to have multiple of those high heat areas, so to say, that it would pick up on? That's kind of what I was curious about, because I don't see in any of this work that they really talk about that. And I without seeing the data, I don't know if that's in there.
The data is available at request if it's not for commercial use. So yeah, you can always get it. But I don't know if I got the question. You mean whether a prototype can represent more than one mass margin type?
Not necessarily. So it's very hard to try to describe it. I guess, so if you take the picture right below activation of prototype on test image on the slide that you have,
yep,
that top one, if you just duplicate the area that is yellow and yep, stick it within that same box, is this model going to be able to process and classify both of those areas within a unique mass margin if they're different mass margins? Like, will it be able to identify multiple cancerous areas rather than just a single one? That's what I'm curious about, because I mean, the nature of cancer is it spreads, and you know, it's not always just centralized in a single location, right? So a real life application, there could be multiple cancerous locations within a single scan. And so I'm curious if this would pick up on that. Was all. Anyway, I might be going too deep on it, but that's all I was trying to think of.
Okay. Yeah, thanks. Thanks for the question.
Yeah.
I was more curious also to know whether you believe in these post hoc versus interpretable by design, which one is better? I understand that this one is more expensive, and when it comes to high stakes domains, maybe you can afford, and maybe you need to create something like this, but it might not be very practical to extrapolate this to some other contexts or applications. So I was curious to know a little bit about that as well, because the authors make a lot of emphasis in saying, hey, make a lot of emphasis saying, hey, this is not a post hoc. We're not using post hoc explanations. Which are themselves kind of unreliable sometimes. We are kind of representing and following the radiologist's reasoning process, blah, blah, blah. So they really create a story around that. Of course, there's a technical part that they do, but I was also curious to know, in the conceptual level, in the intuition level, what do you think about this?
I can share my 2 cents. Okay, first of all, thank you, Mireia, for the presentation. So Yeah, I think, like you said, right, that this post hoc explanation is really useful because, well, it's more applicable, I would say, right, given all these machine learning systems already running everywhere. So post hoc is really, well, useful to at least to in dealing with this tech debt, right? But on the other hand, I don't think it's now already, you know, like building these inherently explainable models. It is already something that we can do reliably, right? So okay, I like what these people do. Is actually something that we have been doing as well. Like, oh, let's figure out what are the pixels, what are the content in this image, medical image, right? That matters to a certain prediction task or classification task. But well, but this is still, I would say, we are still at the very shallow, we're still at the surface. And it's a very shallow understanding of what's exactly going on in the model. Because, but these people, they use the word reasoning as well, but reasoning would imply that it's not only about concept, but also, you know, the logical path it should follow, right? No work can do that now. This work cannot do that either, right? It only shows, okay, these are the things that the model should be paying attention to, but what's going on inside, right? Really, what's going on inside those models? Are these models following the reasoning path? Or, I mean, and to what extent, right? How exactly it matches the doctors, radiologists, and I don't know, those domain experts' knowledge, right?
Yeah, yeah, this is a trick that they use. They constantly say that, like, they mimic the reasoning process. That's why I was using the reasoning process of the doctors, which is not really the truth. I think it's a way of saying, okay, since doctors many times give diagnosis through comparison, through similarity between, you know, a radiography or mammography in this case, that, you know, has a malignant whatever, and the similarity with respect to what you are trying to give a diagnosis for right now. I guess it's because of this similarity-based approach that they say, hey, we are following the reasoning process, once again, reasoning process of the doctor. But it's true that there's a trick there when saying that they're mimicking this kind of reasoning process, which I don't know if it's very accurate to say so, but yeah.
Yeah. I think there's still a huge gap. This is just the first steps, right? And I'm not sure, you know, when we would have a method of building, you know, a rigorous, a solid method for building inherently explainable or reliable models. Yeah, I think it's I don't know, $1 billion question. It takes well 5-10 years at least for people to figure out a good way of doing that. This is something, by the way, we also have been doing for some time. Well, I guess you know that, right? So if there is actually one paper that we did on the natural language processing task that has similar ideas, like finding a way of incorporating human knowledge into NLP tasks by first ask humans to not only label individual sentences for training the model, but also to highlight certain parts of the sentences that are relevant from human perspective, right, for the task, and then make the model learn from both the labels, but also the reasonings. So there's one paper which I'm not super proud of, but it's relevant. Oh, let me share to everyone here.